So, good day students. Let's now look at what you shall achieve in this nugget. The previous nugget had 3 overall aims. First, you should be able to compute the amounts of combustion products from any fuel with a specific elemental composition. That is, the dry substance or dry ash-free substance analysis, with different ash contents and different moisture contents. Then you should be able to compute the amounts of combustion products from any liquid or gaseous fuel with a given composition. And finally, you should be able to adjust the amounts of combustion products with respect to excess air. And to do that, you made yourself a computational tool. Now you shall improve that tool and include an estimate of the adiabatic temperature into it. And then you shall use that to get an impression of what temperatures you might expect in some different cases. Following the previous nugget, you did quite a lot of reading in column 4 in the Busy-Plan handbook, and what you shall do first is to repeat parts of that. The 2 sections 04, 00, 08 and 09 contain short descriptions of different types of boilers in different scales, but they also mention shortly the sensitivity of the different systems. And the ash behavior, you should put special attention into the slagging index, is discussed in the ash behavior appendix, so repeat that too. Disturbances or disruptions in energy supply systems may be catastrophic, and it is quite common that disturbances are ash-related. Just imagine 2 hospitals, one in northern Canada and one in Nigeria. The one in Canada might use district heating from a biofuel-fired energy plant, while the one in Nigeria might well use district cooling from a biomass-fired energy plant. And then suppose the heat supply to the Canadian hospital fails during a winter day when it is 30 degrees below zero. Or suppose the cooling supply to the Nigerian hospital fails on a hot summer day. So what you shall ultimately do in this homework is to do some estimates of slagging indices, and then you shall compare these to your estimated adiabatic temperatures. And the reading you shall do is to help you to fulfill this. Professor Isidoro Martinez at the Polytechnic University in Madrid has collected his lecture notes in a very nice way, and I also suggest you read his notes on combustion thermodynamics. While at his page, you may as well have a look at some other notes, but the one on combustion thermodynamics is what you will need to fully understand what you are doing. When you are finished reading, you make a backup copy of the computational tool from last nugget, and then you start putting in the calculations of the adiabatic temperature. You should take special care to test the CP values calculation. What you have to do is to, one way or the other, numerically calculate the integrated mean value of the gas constituent CP values from your selected reference temperature and to the computed adiabatic temperature. To get that right, you have to have the coefficients and the functions right. So on this slide, I show the overall diagram with the scales. Any programming mistakes tend to result in powers of 10 errors. So if your polynomials produce a diagram like this, then you should be safe. After this, you have a program or something that can compute the maximum attainable combustion temperature of any fuel. Now turn your eyes to the Phyllis database and browse for pine wood properties. I personally find the Phyllis database to be one of the most comprehensive, and I use it extensively. Usually, there is no reason to look at individual values, but averages are almost always to be preferred. At the far right, you see little diagrams with a green line in them, They are to tell you how many samples contain this value, and the diagram is to show how the sample values are distributed between minimum and maximum. Out of all 55 values for pine wood, only 3 measure the initial deformation temperature for the ash and the hemispherical temperature according to the ASTM standard method. So you will be able to compute the slagging index as 1210 degrees C. Now use your computing tool to find which moisture content you would have to get an adiabatic temperature below 1350 degrees C if you are firing the pine wood using 20% excess air and the air is cold. I just picked 1350 from the top of my head because in a real combustion chamber will the maximum temperature be some 150 to 200 degrees lower than the adiabatic. You will find that the moisture content is some 45 to 50% by weight. In case you want pine wood that is significantly drier, then you want to use a combustion chamber that is constructed so that the maximum temperature in reality is, say, 400 degrees less than the adiabatic. So in that case you want to have only thin insulation on the combustion chamber walls. Now do the same for birch woods. Test different fuels that you select from the Phyllis database and consider their slagging behavior and also other aspects such as corrosive properties and the like.